Alrighty, hi folks. I'm Kivigak and I'm here to talk about connecting Chisel and C++, leaning on Yosys for all the hard work. So in the workplace, I'm a systems engineer, which usually means weaving together low and high level languages in dark ways. So like writing Erlang C nodes, combining Ruby, Go, and C++, that kind of thing. And in open source, I'm regrettably best known for my work with Markdown. I have zero electrical or digital background, but after microcontrollers failed to capture my interest, FPGA succeeded, and I started exploring in earnest last year. Now, this is something I do for fun, which meant that Verilog and VHDL were totally capable of like turning me off this path forever. I'm really into programming language theory and design, and like Verilog could sure have used some of either. I found Amaranth pretty quickly, and so I started hacking on Yosys too. I've particularly enjoyed working on CXXRTL, which is the focus of this talk. I spent about 9 months learning with Amaranth, but I'm still this dog and there's a lot more perspectives out there. So I decided to learn Chisel, which is an HDL in Scala, much like Amaranth is an HDL in Python. These aren't high-level synthesis tools. You still just describe hardware in them, but using DSLs embedded in a regular programming language. You write code that generates hardware in a metaprogramming kind of way, except the metaprogramming is regular programming and the programming is circuit definition instead. You run your code and out pops something that can go into your toolchain's front end. Chisel outputs system Verilog, and it's easily configured to avoid constructs that Yosys doesn't like. So we have a Verilog, and we feed it into Yosys. And using the rest of the suite, we can synthesize for ICE40, ECP5, and plenty more. But we can also target C++. Yosys has its own C++ backend, CXXRTL. It's kind of similar to Verilator in some ways, but it has some unique advantages. So for starters, if you're using Yosys anyway, we can avoid adding another tool. And moreover, the C++ comes directly from Yosys's internal RTL model. So you can perform transforms and optimizations and then generate the simulation without a Verilog round trip. It also supports runtime introspection of the design, as well as exposing its API to C. Which makes it feasible to use the generated simulations from any language with CFFI, like Rust or Zig. One of the most fun parts, though, is the ability to instantiate black boxes anywhere in your hierarchy, which you then implement in C++. I'm going to show you real fast what that can look like. Here's a tiny stack machine. It knows how to read and write bytes on UART, some trivial stack manipulation, and how to jump back to 0. The implementation itself is not very challenging, but the important part is that it gets its instructions from asynchronous memory. For unit tests in Chisel, I instantiate a vector like a ROM and implement the other side of the read port, making sure to return data in the write cycle. So far, so good. So let's initialize our instruction memory from SPI Flash. The icebreaker I'm using as a dev board puts its bit stream on one, and there's plenty of room left for user data. So I flash my little ROM into the upper half, and on reset, the Gateware's SPI reader module populates the memory from it before starting the stack machine. But what about our C++ simulation? We have a few options that are more interesting than just ignore the flash reader. So A, we can do like we did with the static memory and emulate the SPI flash in Gateware and put that into the design when elaborating for CXXRTL. This approach is fine for simple external interfaces, but for more complex ones, such an implementation may not be feasible. And writing Gateware for sim means writing test benches for your sim Gateware. And it's also going to run as slow as any other logic. B, we can emulate the SPI flash in C++ by watching the top-level output pins and toggling the input pins as necessary. It's a straightforward approach, but it does mean you have to co-simulate your peripheral at the same time as stepping the design. Or C, we can drop a black box into the design and hook up the SPI reader module to the black box instead of external I/O. And then we implement the black box internals in C++. So this is where CXXRTL's black box support comes in. You give it a module interface definition, and it generates a C++ class for it the same way it would for any other non-flattened module in your design. So then you subclass that, and you implement logic internal to the black box in C++, reacting to events at the simulation step level, without having to rewrite your whole simulation driver into an event loop. This is super powerful, and it's a lot easier to implement a peripheral in full-blown C++ than it is in Gateware. Now, I call this approach a white box implementation to contrast with D, which is take the SPI reader out of the design entirely and drop in a black box which emulates the reader's interface instead. So whereas the white box watches chip select and data in and toggles data out accordingly, painstakingly pretending to be a real flash module, this black box goes one level higher and monitors the read strobe from your design and responds to it directly. So this can really speed up your simulation, particularly if your design clock rate is high, but the peripherals is much lower, like in I2C or something. And as with the other non-gateware options, you can source the data from a file on disk or a buffer compiled in or from the network or whatever you like. It's your C++ code. And so here's the target specific gateware for this example, all on the top level module. Most of this depends on my little framework for Chisel, but it's all just ergonomics and instrumenting Yosys, really. For Icebreaker, we instantiate a real UART driver, wire it up to the I/O pins, and its control interface is connected to the stack machine. The CXXRTL targets just skip the UART and expose the control interface at the top level of the C++ driver. So that's what the C++ simulation interacts with. Similarly, for Yosys, we instantiate the flash reader, connect its pins, and hook its control interface to a wire bundle. The white box also instantiates the flash reader and wires the control interface, but it connects its pins to the C++ white box module instead. The black box skips the reader entirely and instead connects the control interface wire bundle to the C++ black box module. So I really enjoy this approach. It's a lot of fun, and being able to stub out my design at various levels turns out to be really handy as the logic gets more involved. CXXRTL's simulation isn't as fast as Verilator's, but it's in the same order of magnitude. And it lets me make these changes essentially hot swappable because the black boxes are instantiated if and where they occur in the design. And that's it. The main takeaway really is that you can do this kind of thing with Yosys and any HDL. None of this is Chisel specific, it's just what I happen to pick. Thanks everyone.